Why would a stone lying quietly by the roadside know more about the history of Earth than the thickest book in a library? At first, it sounds absurd. A stone is mute, lifeless, and simple. A book is full of words written by people who studied, thought, and recorded history. And yet, geologists will tell you the opposite. If you want the real story of Earth, its age, its struggles, its cataclysms, you should not open a book. You should pick up a rock, because a stone is not just a lump of matter. It's a memory device, a hard drive of the planet, and each layer of its existence is a line in Earth's autobiography. The question is, how do scientists read something that has no letters? Let's start with the paradox. To us, a stone looks eternal, unchanging. You could keep one on your desk for years and it would look exactly the same. But zoom out from human time to geological time, and that same stone becomes a page in a much longer story. Imagine pressing fast forward on the planet. Mountains rise and crumble, seas invade continents and retreat, glaciers grind landscapes flat, volcanoes cover valleys in ash. Through all of that, the stone is there, recording pressure, heat, chemical reactions. Each crystal inside it is like a word etched into memory by physics itself. Unlike books, which humans can edit, burn, or forget, stones carry a record no one can tamper with. Here's a key analogy. Think of a stone as a USB stick. On the surface, it's just plastic and metal. But inside, it stores gigabytes of data waiting to be read with the right tool. For rocks, that data is locked in their minerals, structures, and isotopes. And geologists are the programmers who know how to plug them into Earth's operating system. They don't use computers to read words. They use microscopes, spectrometers, and the laws of physics to read history. When they slice a rock thin enough to let light pass through, suddenly it becomes a stained glass window into the past. You see colors, shapes, crystals that tell you whether it formed in a fiery volcano, in the calm mud of a lake, or deep under crushing tectonic plates. Now let's break down the mechanics. Every rock falls into one of three great families: igneous, sedimentary, and metamorphic. That's like the three main genres of Earth's memory. Igneous rocks are the fiery birth certificates of the planet. They form when molten magma cools and solidifies, whether inside the crust as granite or exploding onto the surface as basalt. Each crystal in an igneous rock tells you how fast it cooled. Big, chunky crystals? That means the magma cooled slowly, deep underground, like a stew simmering for hours. Tiny, glassy crystals? That's a sign of rapid cooling, like lava freezing in seconds when it hits ocean water. Already you're reading a timeline. Sedimentary rocks are more like Earth's photo albums. They form layer by layer from sand dunes, riverbeds, or ocean floors. Each stratum is a snapshot of an environment. One layer might hold ripple marks from waves. Another might carry the outline of a dinosaur footprint. Another might be packed with seashells that whisper, "This was once a beach." It's like flipping through Instagram posts from millions of years ago. Only instead of captions, you get fossils and minerals. The horizontal layering of sedimentary rocks is literally a stack of time, with the oldest at the bottom and the youngest at the top. Geologists even call it the law of superposition. It's Earth's filing system, organized chronologically without any librarian needed. Metamorphic rocks, in contrast, are the rewrite drafts. They start life as either igneous or sedimentary, but then they get buried, squeezed, and heated until they transform. Their crystals realign like words rearranged into new sentences. A limestone can turn into marble, a shale into slate. These rocks tell stories of violence, of continents colliding, mountains crushing them under unimaginable pressure. When you see the swirling patterns of a metamorphic rock, you're looking at the scars of Earth's tectonic battles. It's history rewritten under pressure, but the memory of the transformation itself is still preserved. Here's the moment of clarity. Rocks don't just store things that happened. They record conditions, temperature, pressure, chemistry, that allow scientists to reconstruct entire worlds. For example, tiny bubbles trapped in ancient lava flows contain gases from Earth's early atmosphere. By analyzing them, we learn what the air was like billions of years ago. Sedimentary layers rich in iron oxides tell us when oxygen first flooded the atmosphere in the Great Oxidation Event. Radioactive isotopes inside minerals decay at predictable rates, like built-in clocks, allowing scientists to date events with astonishing precision. A single zircon crystal smaller than a grain of sand can tell us that liquid water existed on Earth 4.4 billion years ago. That's older than the oldest book, older than any word humans have ever written. Let's pause and picture this. You're holding a rock in your hand. To you, it feels heavy, ordinary. But in reality, it's a compressed archive. Inside are atoms that formed in exploding stars before the solar system existed. The minerals may have crystallized in magma chambers beneath ancient volcanoes. The surface may have been scoured by ice during the last ice age. Every scratch, every layer, every trapped element is a line in a diary written not in ink, but in matter itself. It's as if the planet keeps its autobiography not in libraries, but in the very ground we walk on. Think about how fragile human memory is. Scrolls burn, books decay, hard drives fail. Civilizations rise and collapse, taking their records with them. But stones? They sit quietly for millions, even billions of years, waiting for someone to ask the right question. A granite boulder doesn't care if empires fall. A shale cliff doesn't erase itself when languages die. They just remain patient librarians of time. And when geologists read them, they're not guessing. They're deciphering physical codes written by physics and chemistry themselves. The irony is powerful. We write books to preserve memory, but they last a few centuries at most. The planet writes in stone, and those sentences last longer than species. To read a rock is to peek into a timescale so vast it makes human history look like a single footnote. And the more you think about it, the more you realize how humbling it is. We live in the briefest moment of Earth's narrative, yet the ground beneath us carries chapters stretching back to the planet's fiery birth. Now let's move closer to a eureka moment. Imagine a detective trying to solve a case. The witness statements, our books, are biased, fragmented, and written long after the events. But the rocks? They are the crime scene itself. The bullet holes, the fingerprints, the DNA. They don't tell stories in metaphors, they tell them in physics. That's why when geologists want to understand mass extinctions, they don't just read human speculation. They crack open rocks and find thin layers of iridium, the fingerprint of an asteroid impact that ended the dinosaurs. They find ash layers marking volcanic supereruptions that reshape the climate. They find sudden changes in fossils that reveal evolutionary leaps. Each stone is a witness, but unlike humans, it doesn't lie. And here's where the analogy deepens. If rocks are hard drives, then geologists are data recovery experts. They extract information not by plugging in a USB, but by using drills, lasers, and isotopic analysis. They reconstruct landscapes that no human has ever seen, like shallow seas that once covered deserts or forests that thrived at the poles. They read rocks like paleontologists read bones, except instead of a skeleton, they reconstruct entire atmospheres, oceans, and climates. It's less like reading a history book and more like watching a time-lapse film of Earth itself. All of this leads to the astonishing realization: the ordinary stones we step on daily are extraordinary archives. The pebble in your shoe, the cobblestone in a street, the brick in a wall. All of them are fragments of stories older than humanity itself. Some carry the marks of volcanic fires, others the ripples of vanished seas, others the pressure of mountains that no longer exist. They are not silent at all. They are shouting history, if only you know how to listen. One of the most mind-blowing examples of this stone memory comes from tiny magnetic minerals. When lava cools, iron-rich crystals inside it align with Earth's magnetic field, like billions of microscopic compass needles frozen in place. As the rock solidifies, it literally locks in the direction of Earth's magnetism at that time. That means a volcanic rock is not just rock, it's a magnetic photograph. By comparing these snapshots across continents, scientists discovered that Earth's magnetic field has flipped dozens of times, with north and south switching places. Rocks remembered it long before humans invented compasses. Without stones, we would never know our planet's magnetic heart has a restless rhythm. Another layer of memory comes from chemistry. Every mineral inside a rock is like a different voice in a choir. Quartz, feldspar, mica, they each form under certain conditions of temperature and pressure. By identifying them, geologists can reconstruct the environment in which the rock formed. Was it born deep underground where heat and pressure squeeze atoms into tight lattices? Or was it created on the surface where water and wind deposit fine grains? Even the smallest trace elements act like footnotes, hinting at what fluids or gases pass through. A rock is not mute. It speaks in chemical accents, but the most powerful tool for reading stones is time itself. Inside minerals, unstable isotopes like uranium slowly decay into lead at steady rates, like atomic hourglasses. By measuring the ratio of parent to daughter isotopes, scientists can calculate exactly how old the mineral is. Some zircons on Earth are 4.4 billion years old, the oldest known materials from our planet's crust. Think about that. A tiny crystal smaller than a grain of sand has been quietly ticking since Earth's earliest days, outlasting mountains, oceans, and entire biospheres. No human library can match that kind of archive. The more you dive into this, The more you realize that rocks don't just store random fragments of history, they capture global events. For example, there's a thin clay layer found all over the world, rich in iridium, a rare element. It marks the moment 66 million years ago when a giant asteroid slammed into Earth, triggering the extinction of the dinosaurs. That layer is a smoking gun preserved in stone, or consider banded iron formations, massive deposits of iron-rich rock that formed over 2 billion years ago when oxygen first appeared in Earth's atmosphere. Without those stones, we wouldn't even know when life transformed the planet. Each rock is not just a diary entry. Sometimes it's a headline of earth-shaking importance. Now let's zoom back to something ordinary. The cobblestone under your feet may be a piece of basalt from a volcanic eruption millions of years ago. The marble countertop in your kitchen is limestone that was squeezed and baked, perhaps once a thriving coral reef. The gravel on the side of the road could contain fragments that remember when glaciers carved valleys during the last ice age. You don't need to travel to exotic sites to hold Earth's memory. It's literally built into the walls around you, the streets you walk, and the pebbles kids kick along the sidewalk. Once you realize this, you start to see rocks not as dead objects, but as time capsules scattered everywhere. Here's the eureka moment. When we read a stone, we're not just learning about geology. We're learning about resilience, patience, and perspective. A rock doesn't care about kings or wars or borders. It carries memories that stretch across billions of years. To hold one is to connect to a scale of time so vast it makes human history seem like the blink of an eye. And that changes the way you see your own life. Suddenly, your problems feel smaller, but your sense of wonder feels bigger. You realize we are lucky to walk on a planet that writes its own autobiography in matter itself. And there's one more twist. Rocks don't only tell us about the past, they also help us predict the future. By studying ancient climate records locked in sediments, scientists can understand how Earth responded to warming or cooling events. By analyzing volcanic rocks, we learn how eruptions shape the atmosphere and oceans. By decoding the history of tectonic collisions, we predict earthquakes and mountain building yet to come. Stones are not just about memory, they are guides, showing us what might lie ahead. So next time you pick up an ordinary stone, don't dismiss it as boring. Imagine it as a USB drive packed with billions of years of data. See it as a witness to cataclysms and calm periods alike. Understand that you are holding a piece of Earth's autobiography, written not in words, but in pressure, temperature, chemistry, and time. And let that realization spark a little awe. Because while books may preserve our stories for centuries, rocks preserve Earth's story for eternity. If this journey gave you even a glimpse of that hidden autobiography beneath your feet, then you've just unlocked one of the keys to seeing the world differently. And here at How It Actually Works, that's exactly what we do. We collect these keys, curiosity, perspective, and wonder, and share them with you so the universe makes more sense, one surprising story at a time. So give this video a like, share it with a friend who has ever skipped a pebble across a pond without knowing its history, and subscribe to How It Actually Works. Because once you start collecting enough keys, you begin to unlock the hidden library of reality itself, and realize that even the stones beneath your shoes are waiting to tell their story.